Please mute yourself.
Good morning.
Wait a bit. Start in a while. Bhargav, I am unmuting you just to check if everything is fine.
Yes, sir. Everything is fine.
Everything fine. Thank you. You can see my screen?
Yes, sir. Yes, sir.
Okay, great. Thank you. Sorry, somebody raised his hand. So can I get back to him? Mute. Yeah, Divyansh.
सर कैन यू रिकैप वंस की लास्ट क्लास में क्या हुआ था? मेरा नेट की प्रॉब्लम थी तो मैं ढंग से अटेंड नहीं कर पाया था वाली.
Yeah, I'm going to recap that. No problem. Okay. Yeah. Okay, so in the last class, I talked about vector and scalar fields, and we actually visualized them also. So let's go into the recap, and let me choose an example. Yeah. So yeah, thank you for reminding about recording. Okay, so we'll have a recap at what scalar and vector fields could be. Okay, so let's consider we are inside a room, or one of us is inside a room, and we are trying to find temperature inside the room. Okay, so normally we give temperature in terms of a single value like 27 degrees centigrade. Okay, so that is the common temperature that we normally propose. So this is an average value. Okay, average value of a temperature could be 27 degree, but temperature at all the points, okay, all different points inside a room, that can have a different value. Okay, for example, in the daytime, temperature could be slightly more near the doors or the windows. Okay, and could be lesser as you go inside the room, and it is very well actually observable when you have summer, a hot summer. Okay, so in that case, you try to run into the room as quickly as possible and close the door. Okay, so it means temperature near the room is more, temperature inside the room is, so near the door is more, a window is more, inside the room it could be less. Similarly, if you are inside a kitchen, then the temperature could be high near a stove. Okay, and it could be lower everywhere else. Okay. So in that case, we can say that this temperature can be defined as function of x, y, and z. Okay, x, y, and z are arguments. So simple arguments means the coordinates, okay, of any point. Okay, so it means that inside a room, each point in a space can be assigned a different temperature value. Okay, temperature itself is a scalar. So we can say we can assign a scalar value to every point inside the room. Okay, so that means that the room contains a field. Okay, so we have a value being assigned to every point of the room. It means that the room has got a field. Field simply means a ground. Okay, so ground will have something. It will have something like grass. Okay, so at every point you're putting grass, so it's a grass field. If you call it grass field. So same way we can call the room to be a temperature field, or we can say that the room contains a temperature field. And as temperature is a scalar quantity, we say that the room has got a scalar field in it. Okay, so next we can take example of a vector field. Okay, for example, you can consider the same room, and then you can consider an object with unit mass. Okay, and then start thinking about the gravitational force on it. Okay, so that means it the gravitational force normally give that near the Earth's surface, the value of g is about 9.8 meter per second square. And if you then calculate the value of gravitational force, it will simply be m into g, okay, or g, okay, so g Newton. So, however, this is also an average value because you know that the gravitational force will be pointing towards the center of the Earth, okay, and that is why if you move inside the room, then at every point there will be a slight change in the direction of the force, even if you are maintaining the same altitude, okay. But if you slightly change the height, okay, so in that case the value of g will also be slightly changing, okay, it won't be remaining constant. It means that inside the room at every point you can define that force is changing with point. So every point can be defined with a different magnitude and direction of force, okay. So that depends on the location of the object, and we can then consider this force to be a function of x, y, z, okay. So same way as we defined for a scalar field, we can say here that each point inside the room can be assigned a different f value. F itself is a vector. So we can say that the space contains a gravitational force field, or simply gravitational field, okay, or the room contains a gravitational fields or gravitational force field. So this field is referred to as a vector field because each point here is given a vector, okay. So a point which is further away from Earth's surface, that will be assigned a smaller vector, and a point which is near the Earth's surface, that will be assigned a bigger vector, for example. Okay, so then we also went for the visualization of these vector functions, okay. So for example, you can consider a one-dimensional function like gx given by x multiplied by x cap. Okay, so you can see that this function will be increasing as you increase the value of x, okay. So if you draw a vector corresponding to this function, that the length of that vector, the arrow, that should be increasing with increasing value of x. However, direction will remain the same, okay, along x cap. So this gx function can be represented with the help of this arrow. And as this does not depend on y, so obviously these arrows will remain of the same length, or the function will have the same value with different values of y, okay. So this arrow length obviously represents the magnitude, and the tip of the arrow gives the direction. Same way, I also gave you the examples of two-dimensional functions like x cap plus y cap, or even x cap minus y cap, okay. So with this, I hope you are able to understand how a field or vector field or a scalar field or a scalar function can be understood, okay. So next thing that you can do yourself is to consider electric field, magnetic field, and draw electric field of a point charge, okay. So you already know that if you have a point charge somewhere, then the field value will be large near it, and as you go away from it, the field value will be going down. So the field, electric field of a point charge, that should be represented with this kind of arrow. The arrow should be having highest length near the charge, and then the length of the arrow should be going down as you go away from the charge. Okay, so this is all. Let me clear it. Okay, so then I defined, okay, so I told you about the importance of vector algebra, vector calculus, and here we are dealing with vector calculus. So first thing that I want to introduce was gradient. Okay, so to define these gradient, divergence, or curls, which are different operations, okay, or different derivatives in case of vector calculus. So we defined this del operator, okay. So del of a scalar function, this is called gradient. Then del dot a, where a is a vector, okay. Del is also defined as a vector, though it's not though it's not a normal vector. Okay, so del dot a is then defined as the divergence, and then del cross A is defined as the curl. So here A and del both are vectors. This f here is a scalar function. Okay, so I then give you a flavor of what ordinary derivative is. Okay, so ordinary derivative represents how a function varies at a certain point. Okay, with uh, increasing or decreasing value of its argument like x. Okay, so df it can then be written as df over dx multiplied by dx, where dx is changing x, and df over dx gives you the rate of change. Okay, so next thing that I hope you know is partial derivative. So in case of partial derivative, the function f, okay, it can have arguments x, y, or even z. And in that case, when you take the derivative, okay, like with respect to x, you consider all other arguments to remain constant. Okay, all other variables to be constants. Okay, so we represent it this derivative with del rather than d. Okay, so then partial derivative of function f with respect to x, okay, keeping y and z constant. So that is written as del f over del y. Okay, instead of df over dy, which represents the ordinary derivative or full derivative, as you call it. Okay, so in case of partial derivative, when you take that of function, you consider all other variables to be constant. You take the derivative with respect to only one. So if you want, you can go to this YouTube link. The partial derivatives are very nicely explained there. And then you might also try to uh, extend that definition over this surface, okay, which I have shown here. Okay, then I defined the gradient. Okay, so gradient was defined with the help of this equation, where dt is basically change in some scalar function t. So this change in scalar function t can be given as del of t dot dl. Okay, so dl here is a displacement vector. So then I tried to give a interpretation or geometrical interpretation to it. So how did we do that? We considered just a moment. Okay, so to give gradient an interpretation, I wrote dt as del t dot dl, which can also be written as magnitude of del t magnitude of dl into cosine theta. Okay, so now if you fix the value of dl and search around all the directions, okay, to get maximum value of dt. So that means that you are changing the value of theta. Okay, so with that, it is obvious from this equation here that this dt will be maximum for theta equals 0. Okay, so for dt is maximum for theta equals 0. So we can say here that this change dt is maximum when del t is pointing in the same direction as dl. Okay, so in that case, we can say it otherwise also. If del t points in the same direction as dl, which means theta equals 0, then the change in this function t is maximum. Okay, so that way we can say that this del t points in the direction of maximum increase of function t with respect to l. Okay, so as you increase dl, the maximum change in dt happens in the direction of del t. So the magnitude of del t is basically the slope or rate of change along this maximal direction. Okay, so for example, uh, okay, so this is all right. Okay, so I have an example here. Before that, let me move this. Yeah. So suppose you are standing somewhere at this hillside. Okay, so suppose uh, there is somebody at this point here. Okay, now standing here, he or she can see that there is an increase in height along this direction, okay, or along this direction, or along other directions too. Okay, so however, the maximal increase in the height of the hill occurs in this direction. Okay, so we can say here at this point that gradient is pointing in this direction of the red arrow at this point. This direction here is not the direction of maximal increase of height. Okay, even this direction is not maximal increase of height. Similarly, this is not. Okay, similarly this one. So maximal increase of height occurs in this direction. So we can say that this red arrow basically represents the direction of the gradient. Okay, so same way, if you at some point have del t equals 0, okay, say at xyz, then that function is called to be a stationary point, okay, of function t. So for example, if you take the summit, okay, or the peak of a hill, so at that point, if you change xyz slightly, then this t function won't be changing much. Okay, it means that this del t, okay, it has 0 value for slight change in xyz at xyz at the point xyz which lies at the peak, okay, or even at a for example a valley. So okay, so uh, gradient is basically a vector quantity, even if we are operating this del operator on a scalar function. Okay, so it will have a magnitude as well as a direction. The magnitude will give you how quickly the field is changing at any point in space. Okay, and the direction will be given by the direction in which field is increasing most quickly with the distance. So same way like height of a hill here. So we can take one more example other than that I gave you that day. So we can consider a plane, for example, given by psi x comma y equals 5x plus 2y. I hope you know the equation of the plane. So if you take the gradient of this plane, then it will be del of psi. So you will have I del over del x of psi x comma y plus j del over del x of psi. So that should give you the value 5i plus 2j. Okay. So we can here observe three things like we have defined. So even though this psi is a scalar function, its gradient is obviously a vector. It has got x component, it has got y component. Now we can see the second thing, that this x component has a value which is twice as large or more than twice the size of the y component. What does it mean? It means that the tilt of the plane is steeper in x direction as compared to the y direction. Okay. And the third thing is that if you want to calculate slope in any direction, okay, in the direction of the gradient, then the slope can be given by the magnitude of this function. Okay, so also magnitude of del psi. So it will simply be square root of 5 square plus 2 square raised to half. Actually, it should come out to be 5.39. Okay, so we have somebody. Anishwar. Oh, sorry. I lowered your hand somehow. Anishwar. Yeah.
Sir, how can
Yeah,
we say that
please.
xi is a scalar function?
Uh, Actually, we are defining it to be a scalar function. Okay, unless we have a proper interpretation for it, we cannot say if a function is a scalar function or a vector function. Okay, like at the start of today's lecture, I gave you example of temperature inside a room and
Yes, sir.
gravitational force inside a room. Okay, so then
Hmm.
if this psi is a function of temperature type, then it will be a scalar function. If it is some function of uh, force type, okay, if
Okay,
function
sir.
that, yeah, that is function
Okay,
of
sir.
the
Got it.
force.
Thank you, sir.
Yeah,
Got it.
so you should have proper interpretation for it then. Okay, so if I want to then uh, represent or visualize this plane psi x comma y 5x plus 2y, then you will expect that it will have a steeper rise along x direction as compared to y direction. Okay, which is gradient shows. So then I have shown it here. So you have x axis on this side and y axis on this side. So you can see the value of the function is increasing more quickly as you increase the value of x as compared to the value of increase of y. Okay, so it is obvious that this gradient, which has got a higher bigger component along x, will have the function will have correspondingly the function will have a steeper increase along x direction. Okay, so if you want to find out maximum uh, increase direction, where will it be? Should be somewhere in the direction of 5y plus 2j. Okay, so it may be given for example by this line. Okay, so here you will see the maximum increase direction or the direction of the gradient. Okay, sorry, right. Yes, Raghav. Raghav, please unmute yourself.
Sir, why we are taking temperature function as a scalar function?
Temperature is scalar function. So, do you think temperature is a vector quantity? Mute yourself. Raghav, are you okay? Yeah.
Yes, sir, because temperature. Yeah, yeah, sir. Sir, because
So,
I think temperature has different direction at every point. Somewhere high,
different.
somewhere low. So why we are not taking as vector?
Somewhere high, somewhere low. High or low, their values, right? One magic. So, high and low values, they do not give uh, the direction. Okay.
Yes, sir.
Values basically mean the scalar also has got a value, right? The value could be high,
Yes,
the
yes.
value could be low. Okay, so same way the temperature could be given with a single value at any point. So that is why we call it a vector. Okay, in simple meaning, though vector is defined in other terms also. Okay, so you have to take care. Okay, so sorry. Okay, so I gave you other examples like r x comma y of x square plus y square. X square plus y square, if you consider a 2D plane, so it can also be written as r square, and then you will get the same thing as r. So when you took gradient of it, we found out that it was r cap. Okay, so what does it mean? That the gradient is pointing radially outward, and we can also draw it like in the diagram shown here. Okay, so it means that the gradient is pointing radially outward. What does it mean? That the distance from origin increases most rapidly in the radial direction. Okay, because this del r gives the direction of the maximum increase, okay, or maximum change. So obviously this r, which is distance, so distance will increase most rapidly in the radial direction. So that is also obvious from this function, okay, which I have plotted at the top here. So same way, you can also try to interpret this function here. So you can see when you have x and y equals 0, okay, for this function here, uh, and you take the gradient. So for x and y equals 0, you will see that this del g equals 0. So what does it mean? It means that there should be a peak point, okay, or a dip at that point as x comma y equals 0. And at all other points, you will get a finite value of the gradient. However, if you take large value of x and y, what happens then? So for that large value, you will see you have a negative sign here. Okay, so that large negative value is obviously the lower value. Okay, so if you take a smaller value near x comma y equals 0, okay, so x and y both 0 comma 0. So if you take a small value near that, then obviously you will understand that this del g will have a larger value. So near the point 0 comma 0 here, I have shown larger vectors, and as you go away from them, you're getting the smaller ones. Okay, so if you want to draw these xy curves, okay, so then you have to consider the xy plane and then the value of the function along z plane. Okay, so for example, if you want to plot height of a hill, okay, so that can be considered as z, and it will be a function of x comma y. So for example, at x equals 1, y equals 1, say height of the hill is 20 meter. Okay, then x equals 0, y equals 1, you have some height, you will get this value. Similarly, for all other values of x and y, you will have the z values given. Okay, so then you will take this x axis, y axis, and z axis. Okay, and at all these, like suppose I have x equals 1 here, y equals 1 here. So at x1, y1, you will put some value here of the z, like 20 centimeter. And x equals 0, y equals 1. Okay, you will have certain point, and you will put this the value of z again. Okay, but normally these curves are drawn with the help of softwares, okay, or apps. So you put these values of x and y in that software, feed them, and that software will give you the plot, okay, or you will extract the plot from that software. Okay, so I have an example here, which is also given in the Griffiths. The height of a certain hill is given with the help of this function h x comma y. Okay, where y is distance in miles north, x the distance east of South Hadley. Y is the distance in miles north, and x is the distance in east of South Hadley. Okay, so we need to find out where is the top of the hill located. So how to do it? At the top of the hill, you know, gradient of a function should be 0. Okay, so you will calculate gradient, and then you will equate it to 0, and then you should be able to find out the value of x and y. Okay, so for that matter, I have put the value of gradient here. So in the gradient, you will have a x component, like shown here, and then you will also have a y component. Okay, and if del h is 0, it obviously means that this x component as well as y component, both of them should be 0. So with that, you will get two equations, and when you solve these two equations, you will get the value of x and y, and that should give you the location of the hill. Okay, now how high is the hill? So how to get how high is the hill? So you know the location of the peak, okay, or summit of the hill. So x comma y, and at this point x comma y, this h value should give you the height of the hill. Okay, so you already have these coordinates x comma y, and then you should put these values in the hx comma y, and you will get the height. So how steep is the slope at point 1 mile north at 1 mile east of South Hatley? Okay, so you will correspondingly get the coordinates. 1 mile north should be x equals 1, and sorry, 1 mile north should be y equals 1, and 1 mile east should be x equals 1. Okay, so you have the coordinate x equals 1, y equals 1, and then you have to find out steepness of the slope. Okay, so you will calculate the gradient at that point. Okay, so next thing that I'm going to define here is divergence. So what is divergence? Divergence is of a vector function or a vector field. V is given by del dot B. So it is like a dot product of two functions. Okay. Dot product of two functions is given by a vector A dot vector B. So same way, instead of vector A, we have del vector here. So del dot B is x cap del over del x plus y cap del over del y plus z cap del over del x. And similarly, we can write this function B in terms of its x, y, and z components. Okay, so that way this del dot B equals del bx over del x plus del by over del y plus del bz over del z. And I hope you can understand here that this del dot B will be a scalar quantity. Okay, so if you want to understand the geometrical meaning, so this del dot B, as its name suggests, it is a measure of how much a vector B spreads out from a point in the question. Okay, so you will define this del dot B at certain point, and the measure of spreading out of that function B will give you the divergence. Okay, so for example, I have these functions here, like the function shown in the first diagram on the leftmost side. Okay, so you can see that this function is represented with the help of these arrows. So it is obviously a vector function, and it is increasing in the radially outward direction. Okay, so we could even represent this function probably with R function. I don't know. Okay, so that value of R should be increasing with increasing value of R. So we can understand here that at this point, the center, we see that the function is diverging away from this point. Okay, or we can say that the function has got a positive finite divergence. Similarly, if you have these arrows pointing in the other direction, like in the diagram at the mid, so that kind of function is actually converging at a certain point. So at that point, we can say that the divergence is negative, okay, or the function is actually converging to that point. For this function in the third diagram, the divergence could be divergence is 0. Okay, so this function here, you can understand it this way, that this function has got an increasingly higher value. Okay, if you consider this point, for example, at this point, okay, it has certain value, then it is actually increasing in the upward direction. So even this function has got a positive divergence. Okay, so you could understand it in one more way. So suppose you are standing at the edge of a pond, okay, some pond. So suppose this is pond and somebody is standing here. And suppose he puts some paper pieces or probably chalk powder in the water, and at the point, okay, or at the location where the chalk powder has been put, if the chalk powder starts to spread out, okay, or the paper pieces start to spread out in the water, then we can say that the location where the person has put the chalk powder or the paper pieces, that is the location of positive divergence, okay, or that has got a positive divergence. Similarly, if these paper pieces start to get collected at one point, then we will say that the location has got a negative divergence, or the paper pieces will be converging to one point. So a point of positive divergence is also called a source or a faucet. Faucet, I hope you know, it is a tap, water tap, okay, from where water comes out. Okay, so from this water diverges. So we can say that the source, okay, or a point of positive divergence is basically a source or a faucet. Then a point of negative divergence is basically a sink, okay, or a drain. So like the point from which water goes out, okay, so that has got a negative divergence. So you can also consider a positive and a negative charge, and then think about electric field. Okay, so we say that the field lines actually spread away from a positive charge. So we can say that the electric field will have a positive divergence near a positive charge. Same way, the electric field may be considered to have a negative divergence near a negative charge. So positive charge is basically a source or a faucet of electric field, and negative charge can be said to be as sink of the electric field. Okay, so yeah, very. We can take an example here. For example, where we have a vector function VA given by R. Okay, R vector again. So R vector can be written as x cap plus y cap plus z cap. And I hope you can understand that this is a radial vector. So radial vector should have a positive divergence, because the value of R will increase as you go away from a point. So this should have a finite divergence. However, if you take other functions like VB equals z cap or VC equals zz cap, so in that case you can understand that these functions, they are not diverging functions. Okay, so they should have a zero divergence. Oh, not the third one, obviously this one. So zz cap obviously is diverging, because as you increase the value of z, then this function value will also be increasing. Okay, so next thing is curl. So curl of a vector function v is given with del cross v, and del cross v, like the normal cross products of two vectors, is given with can be given in this determinant form. So we'll have x cap, y cap, z cap for the components, and then del over del x, del over del y, del over del z for the components of del, and then vx, vy, vz for the components of v. So this can then be written as this summation here of x, y, and z components. Okay, so curl, like normal cross product, is a vector quantity, and its direction can be given with the right hand rule. Okay, so like divergence was a measure of how much a function diverges from a point, the curl is a measure of how much a vector swirls around, okay, or how much a vector curls around a point in the question. So for example, if you consider this point here, okay, and consider these vectors, okay, so suppose they are velocity vectors or v vectors, so then you can see that these vectors are actually curling around this point here. And if you try to give the direction to this curl, then we'll point our fingers, okay, fingers of our right hand, in the direction of these arrows, and the thumb will give you the direction of the curl. Okay, so that way this curl of the field, okay, or the function given by these arrows, that will be pointing in the z direction. Okay, So this function here has got a finite curl. Similarly, this function here has also got a finite curl. But if I take these functions, okay, like here, or the field lines like here, do they have any curl here? They are not curling at all. So we'll say that this field lines should have zero curl, okay, or del cross E, that should have a zero value. Okay, so this you can understand with the same logic as standing near the edge of a point. So if you float some pedal wheel or you put some plastic wheel inside the water, and if it starts to rotate, okay, so if you place some wheel inside the water which is near you, and the wheel starts to rotate, then we can say that the point you have placed the wheel at has got a non-zero curl. Okay, a whirlpool, I hope you understand what is it. So इसको भंवर भी बोलते हैं हिंदी में. Okay, so a region of whirlpool or region of भंवर inside a river. Okay, so that has got a large curl, obviously. Okay, so same way we can consider an example here. We have a vector function VA, which is given by negative y x cap plus x y cap, and this can be actually visualized with the same diagram as shown earlier. So if you try to calculate curl of this vector VA, then you will use the determinant, and then you can find out the value of the curl. Okay, so this here you can see that this okay, so this function, for example, the curling function here, can be represented with this equation. Okay, and then as shown in this diagram here, the curl should be as evaluated from the right hand rule is pointing in the z direction. And when you do this calculation, the actual calculation of del cross VA, you see that it is still pointing in the z cap direction as expected. Okay, so same way you can also do this calculation for x y cap, and then you will see that this function is, the curl is pointing in the z cap direction. Okay, so that is all from the today's lecture, but I can probably take an example. Okay, so for example, we can have a river. Okay, just to give you, and we can have water flowing in it. Okay, so there is water flowing in this river, and then you will expect that the speed of water will be low near the banks. So if it is a bank here, then the speed of water should be low near the bank. It should be maximum at the center. Okay, so if you want to represent the speed of the water, then that can be represented with these arrows here. At this point. Okay, so so if you start at this point, for example, and you look in this direction, you see that the speed is increasing. Okay, the value of v should be increasing in this direction. So, or this value of, or the v should be having higher values, increasingly higher value, it means at this point here, you should have a positive divergence. Similarly, at this point, you can expect to have a positive divergence. Now, if you put some wheel, for example, here, okay, suppose this is a wheel, then at the for the portion which is near the center of the river, the velocity is higher in this direction. Okay, and for the portion of the wheel which is near the bank, the velocity of water is lower. Okay, so these two velocity vectors can also be considered like we have at this point we have a velocity vector in this direction, and at this point we have a velocity vector in the opposite direction. So with this kind of velocity of the water, the wheel should start rotating, okay, if the river is flowing. So we can say that at this point here, it will have a finite curl, okay. Even though, so this wheel should start rotating anti-clockwise here, and if you put the wheel on the other side, like here, the wheel will start rotating in the other direction. Okay, so if you consider this curl to be positive here, then this curl should be negative. Okay, so this will obviously be anti-clockwise direction, and this here is the clockwise direction. Okay, so yeah, and this is where I would like to end. If you have any queries, any questions today, you can ask me.
Sir, can you please explain the last example once again, sir?
Which example?
Sir, the bank and the wheel one.
Bank and the wheel. Okay. Near the bank, okay, banks are actually they have soil, and soil is stationary. Okay, so whatever comes in contact with the stationary thing, because of the inertia, that will also like to be stationary. Okay, so this water can be considered to be made up of different layers. Okay, and then the layer which is far away from a stationary thing, that can be considered to be moving faster, or that will be moving faster than the layer which is in contact with the stationary object here. Okay, so this V will have a higher value here. And then if you put a wheel, a big wheel, something like this, then obviously the water velocity at this point is higher. So this water will try to take this portion, okay, with a higher velocity towards right. Now, the water which is at this point will be trying to take wheel with a lower velocity. Okay, so it means the point here will be trying to go faster, and the point here is going slower. So obviously the wheel will be trying to rotate this way. A wheel may start rotating that way. If you put the wheel other way, so in that case the wheel will obviously be going in the or rotating in the other direction. So is this okay now? Who was it? I forgot. Who was it? Dev, right? Okay, so I don't see your hand now. Dev Sharma. Yeah. Yes, Dev.
sir.
Okay.
Clear.
So no other query?
No, sir. Thank you, sir.
Yeah, Sandeep.
There's some practice question assignment.
Hello. Could you please speak louder?
There's some practice question and assignments.
Practice question. Okay. So practice question you will get. You will get them soon. और आज आपका tutorial भी होगा. Okay, time पे. So be present for that.
Okay.
Lower your hand. Yeah. Shubhrant.
Yes, sir. I wanted to ask why
Yeah.
the curl of conservative force is always 0.
So curl of conservative force is always 0. Non-conservative force is non-zero, right?
Yes, sir.
Okay, so how to give it? Actually, uh, you could wait till the next class. Okay, so then I will be defining curl in terms of line integral. Okay, and with
Okay, sir.
that line integral, it will be easier for you to see that it should be 0. Okay,
Okay, sir.
the physical interpretation, I do not have it in my mind. I will think about it and let you know. Okay,
Okay, sir.
Rajat, is there
Yes,
anything,
sir.
Rajat? Yeah,
So you gave an example.
yeah.
Yes, sir. So you gave an example of water flowing out from a bottle.
Not bottle, actually faucet or tap. Tap.
Yes, sir.
It was a tap.
So,
Yeah.
sir, why it
Yes.
is a negative divergence?
No, it's not a negative divergence. Okay. So if it is a faucet or a bottle and the water flowing out from it, then obviously these water molecules, they will be diverging away from each other. So it should have a positive divergence. However, if you have a sink, okay,
Sir, but
the sink of your
yes, sir.
kitchen, okay, so in that case, the water should be flowing, all the water should be flowing into it. So in that case, we can say that the water is converging towards one point, and that should have a negative divergence then.
So, but we know that when water flows from a tap,
Yes.
it somewhat converges. It has a streamline flow and it converges.
No. Actually, when it comes out of the tap, okay, it is diverging. The water molecules that they will try to get away, okay. But when the water actually falls down inside the sink, at that point on the surface of the sink, it will be moving towards this common point, okay. So the drain
Sir,
point.
I have another doubt. I'm saying that.
Yeah.
Hello.
Yes, go ahead.
Sir, I was saying that when water comes out of the tap, when
Yes.
it just comes out of the tap, it converges itself in a streamlined flow towards the inner end. So, sir, won't it be converging?
Before coming out. So if you say here, then suppose this is the tap, okay, and suppose I represent water molecules with these arrows. Is it okay? So do you mean at this point here?
Yes, sir.
Do you mean
Sir,
at this
at
point?
the end of the tap, at the mouth of the tap.
At the
at the
end of
mouth
the
of the tap.
tap, yeah. So here, the water molecules, they will start diverging. So why I'm unable to understand why you are thinking it to be converging. Okay, away from this point. But towards this point, okay, towards this point, when you are approaching it, so at this side, you might say that there could be a negative divergence from the tap side. Okay.
Sir, I'm not saying that thing. I am saying that at the end of the
Away,
tap, means
away
at
from.
the mouth of the tap.
Yes.
Yes, sir.
Yeah.
So the vector will be in the opposite direction. The outer vector which have you drawn,
Yes.
it will be in the opposite. It will be in
Opposite
the
to
inner direction.
Opposite to what? The vectors.
Sir,
Okay.
can you please allow us to annotate?
Just a moment. So I am trying to explain it in the terms of velocity of the molecules.
Yes, sir.
Yeah. So now you go ahead.
So can you allow us to annotate on the screen?
Just a moment. Yeah, go ahead.
So like it is the tap.
Okay.
And when the water comes, it comes in this way. So it comes out in this way. So after coming out from the tap, the water converges. So
Okay.
is it not a negative divergence?
If it is this way, then obviously it should be. Okay, because the water should be trying to converge like this. Okay, however, it will also depend on the flow. Okay, so if you have a low flow, in that case, you might see a stream coming like this. But if a lot of water is flowing, then
Yes, sir.
in that case, it could be opposite. Is it okay, Rajat?
Yes, sir. Thank you, sir.
Uh, Mohnish,
Hello, sir.
yeah,
Can you show the slide where you defined curl?
just a moment. Sorry. Yeah, yeah, 0.
So the second row of the matrix determinant.
Yes,
So it is the partial derivative of that function, right?
yes,
So it should be in the second line. It should be Vy into del V by del x, right?
just a moment.
Vz into del V by del y minus Vy into del Vy by del z x cap.
X cap into del
So
V. So if you take X cap, then obviously this will go away. You will have del Vz over del Y minus del over del Z of Vy. Is this wrong?
but what is this term del by del y?
Del over del Y. This is actually partial derivative of B.
V,
So,
right?
like I told you earlier, B could be a function of X, Y, and Z.
So the
So
term
when you are
should be right
when you
actually.
are when you considering del over del Y, it means you are considering Y and Z to be constant. You take only derivative of B with respect to X. Okay, and forget about Y and Z, or consider them to be constant merely. Okay, like
So it's basically Vz into del V by del y, right?
Vz into
Del V by del y minus Vy into del V by del z.
no, I am unable to understand you.
So I'm saying that first
Yes,
in the x cap, for x cap the
yes.
coefficient should be Vz into del V by del y minus Vy into del V by del z.
Why?
So what is del Vz by del y?
Okay, so suppose you have this B given by X Y square into Z. Okay, then this del B over del X. Here
Y
X,
square
Y,
z.
Z, they are all variables in as we consider normally. Okay,
Yes.
so if you have to differentiate this B, then you should consider all of them variable. However, when you take the partial derivative, you with respect to X, so you consider Y and Z to be constant. So with that, we will have Y squared Z constant, and we will get only del of X with respect to X. And then you know this del X with respect to X is 1. So we will have Y squared Z. Same way, if you take del V over del Y, okay?
So actually
So that
that's
should
not
be,
my doubt.
yeah. What is your doubt then?
So what is del Vz by del y?
Del Vz over del Y. Okay. So this is basically, you can say the rate of variation of Vz. Okay.
Okay, sir, I got it. I
Yeah.
understood.
Yeah. Okay, then who's next? Yes, Divyansh, anything?
सर डाइवर्जेंस में आपने जो सेकंड एग्जांपल दिया था पॉजिटिव का
Yes.
ये
this
कैसे
one.
होगा ये कैसे हो सकता है? आपने जब कहा था कि डाइवर्जेंस केवल पॉइंट से लेते हैं एक।
Yes, divergence का point से लेते हैं. Okay, just a moment. Now, suppose I give you only these arrows. Consider only these arrows from this point. Okay, so what do you think? Is the function is still diverging or the function becomes non-diverging?
Still diverging.
Obviously. Okay,
Okay,
so
Yes, I got it.
anybody else here? Dhruv?
Yes, sir. I want to know that is. Yes, sir. Am I audible?
Yes, yes, yes. Yeah.
So
Yeah,
I
Dhruv.
want to know, is there any logic behind getting the direction of curl by the determinant method?
Actually, this is how curl is defined. So this is basically the definition. Okay, so del dot b or the dot product of del with a vector field, vector function is called divergence, and the cross product is called the curl. It's basically the definition.
Okay, sir. And thus, in the determinant, the second column, second row is for partial derivative.
Yes, yes, yes. Second row we show partial derivatives.
Then, sir, del Vz by dy means Vz is only the vector in the z direction. Then how can we differentiate with respect to y?
Okay, sorry.
It is in the particular direction.
Right. It's in particular direction. Okay, but this Bz can also be a function of y. Like if you have b given by xy square I cap plus yz square j cap, okay, plus xyz k cap. Is this okay?
Yes, sir.
So this component here will be Vx, this component will be Vy, this component here will be Vz. And now you can see this Vx, Vy, Vz, they do not just depend on x. Even though they are along x, they may depend on x and y. Okay, they may depend on y and z, or they may even depend on all x, y, z.
Okay,
Okay.
sir. Now I got it.
Okay, thank you.
Thank you.
So I'll end the meeting here then. Stop share.